Something out there is breaking the rules. Not theories, not speculation. Actual observations, recorded by telescopes and confirmed by scientists around the world. A radio signal 30 times stronger than the background noise of space. It lasted 72 seconds. Then it vanished and never came back. A star dimmed by 22%. Jupiter only blocks 1% of our sun's light. Nothing we know should cause a drop that massive. Structures stretching over 3 billion light-years across. Our models say nothing larger than 1.2 billion light-years should exist. What happens when the universe refuses to fit inside our equations? There is a star 190 light-years away. Its calculated age is 14 billion years. The universe itself is only 13.8 billion years old. These are not fringe claims. These are measurements, peer-reviewed data from our best instruments. And the strangest part is this: as our telescopes improve, we do not solve these mysteries. We find more of them. The universe is not getting simpler. It is getting stranger. Every new generation of instruments reveals objects that should not exist, signals that should not repeat, voids that should not be so empty, stars that should not still burn. We are not running out of questions. We are drowning in them. And perhaps that is exactly as it should be. If you enjoy what comes next, hit that like button and subscribe. We begin now. It was a quiet night in August of 1977. Jerry Eamon sat at a desk, flipping through computer printouts. Page after page of numbers and letters. Cosmic static, background noise from the universe. Routine work. Then he stopped. One sequence caught his eye. 6 characters in a column that shouldn't have been there. He grabbed a red pen and circled them. In the margin, he wrote a single word. Wow, that printout still exists. You can find photographs of it online. The red ink has faded slightly over the decades, but the word is still legible, still asking a question no one has answered. The signal came from the constellation Sagittarius. It arrived at 1420 megahertz. This is the frequency of hydrogen, the most common element in the universe. Every star, every nebula, every gas cloud contains hydrogen. It broadcasts at this frequency naturally. If you wanted to send a message across the cosmos, this is the channel you would choose. It's like sending a message on the one radio station every civilization would be tuned to. Big Ear was the name of the radio telescope that caught it. A flat reflector the size of 3 football fields, sitting in an Ohio cornfield. It had 2 receivers pointed at the sky, scanning the same region of space 3 minutes apart. Think of it as having 2 witnesses watching the same spot, one after the other. The signal hit the first receiver perfectly. Strong, clear, distinct. 3 minutes later, when the second receiver swept across that exact same location, there was nothing. Silence. The sky was empty. Whatever sent that signal either stopped transmitting in those 3 minutes, moved out of view, or was never there in a way we understand. That brief window between detection and silence is where this mystery lives. Actually, I should be careful here. When I say it looked artificial, I don't mean we know it was artificial. I mean it had all the characteristics we would expect from an artificial signal. That's a different thing. The honest answer is we don't know what it was. But consider what made it suspicious. Natural radio sources are messy. They broadcast across a wide range of frequencies at once. Stars, quasars, pulsars, they all spray radio noise across the spectrum like someone dragging their hand across piano keys. The wow signal was different. It was narrow, precise, like someone pressing a single key and holding it. For 50 years, astronomers have searched that region of sky again and again. Different telescopes, different decades, different technology. They found nothing. The signal has never returned. In 2016, an astronomer named Antonio Paris proposed an explanation. 2 comets had passed through that region of sky around the same time. Maybe their hydrogen clouds created the signal. The hypothesis made headlines. Some people thought the mystery was solved. It wasn't. Comets do emit radio waves, but they emit them across a range of frequencies, broad and diffuse, like static. The wow signal was surgically narrow, a single frequency, clean and sharp. Comets don't do that. Nothing natural we know of does that. The comet theory doesn't fit the data. the mystery remains genuinely unsolved. Here is the frustrating part. We have exactly one detection, one printout, one moment captured on paper nearly 50 years ago. You cannot build a theory from a single data point. You cannot rule out equipment malfunction, atmospheric interference, or pure coincidence. Not definitively. Not with just one observation. It's like receiving a phone call from an unknown number. The phone rings once. You hear something on the other end, but you can't quite make it out. Then the line goes dead. You can analyze that ringtone forever. You can study the static. You can calculate the exact moment it happened. But without another call, you will never know who was on the other end. The wow signal rang once, then silence. Every few years, someone proposes a new explanation. Satellites, terrestrial interference, random noise that just happened to look meaningful. Each theory has flaws. None of them fully account for that narrow frequency, that precise duration, that single appearance, followed by decades of nothing. The Big Ear telescope was demolished in 1998. A golf course expansion needed the land. The instrument that captured humanity's most tantalizing radio signal was dismantled and replaced with grass. Jerry Amon spent years searching for another signal like it. He never found one. He passed away in 2022, the mystery still unsolved. Maybe something was trying to communicate that night. Maybe it was a glitch in the equipment. Maybe some natural phenomenon we haven't identified yet can produce that exact signature under precise conditions. The universe is vast enough to contain explanations we haven't imagined. But there is something haunting about a message that arrived only once. Something that makes it feel less like a scientific puzzle and more like an interrupted conversation. A voice that spoke a single sentence, then fell silent before we could respond. The data sits in archives. The printout sits in a museum. The question sits in our collective imagination. 50 years of waiting, 50 years of listening, 50 years of silence from that corner of Sagittarius. The signal itself lasted just over a minute. The mystery has lasted half a century, and we still have only one data point to work with. One moment frozen in time. One observation. That's all we have. One narrow signal captured on a summer night nearly 5 decades ago. And that single data point has haunted astronomers ever since. This is one of the deepest frustrations in science. The wow signal presents a problem that goes beyond the mystery itself. It touches something fundamental about how we understand the universe. How do you study something that happened once and never repeated? How do you build knowledge from a sample size of one? Imagine trying to determine if a coin is fair by flipping it exactly once. You watch it spin through the air. It lands. Heads. What have you learned? Almost nothing. The coin might be perfectly balanced. It might have heads on both sides. It might be weighted to land on heads 99 times out of 100. That single flip tells you the coin exists. It tells you what happened in that moment, but it reveals almost nothing about the coin's true nature. The wow signal is that single flip. We caught it. We recorded it. We know it happened, but we cannot run the experiment again. Science depends on reproducibility. This is not a preference or a tradition. It is the foundation of how we separate real phenomena from coincidence, from error, from wishful thinking. When a physicist claims to discover a new particle, other laboratories must detect it too. When a biologist identifies a new species, other researchers must observe it independently. When a chemist describes a reaction, others must be able to recreate it. This is how knowledge becomes reliable. This is how hypotheses become theories. A one-time event offers no such luxury. You cannot test it. You cannot verify it. You cannot distinguish between a genuine signal and a glitch that happened to look meaningful. For more than 50 years, astronomers have pointed telescopes at that same region of sky. They have used better equipment. They have listened longer. They have searched with more sensitivity than the original detection could have imagined. They found nothing. The sky in that direction has remained quiet. Whatever produced that signal, if it was real, has not spoken again. And then there is the instrument itself. The Big Ear radio telescope captured one of the most tantalizing signals in the history of astronomy. It gave us a mystery that has inspired generations of researchers and dreamers. It represents our first possible brush with something beyond Earth. That telescope no longer exists. The land where it stood was needed for something else. The reflector was taken apart. The receivers were removed. The entire structure was dismantled. In its place, there is now grass and sand traps and fairways. The instrument that heard what might have been a voice from the cosmos was demolished to build a golf course. Let that sit for a moment. Somewhere in Ohio, people hit small white balls across carefully maintained turf. They walk the same ground where we once listened to the stars. The contrast is almost absurd. Cosmic significance reduced to a weekend hobby. A window into the unknown paved over for recreation. This is not a criticism of golf courses. It is simply a reminder of how easily we move on, how quickly the remarkable becomes ordinary, how institutions and priorities shift while mysteries remain unsolved. The problem is not that we lack technology. We have far better telescopes now than we did in 1977. We can listen to more frequencies. We can scan more of the sky. We can process signals faster and filter noise more effectively. Our tools have improved dramatically. The problem is that we lack repetition. We lack a second data point. We lack the ability to compare and confirm and test. Some scientists have proposed explanations. Each theory attempts to account for the signal's characteristics. Each one has flaws. None of them fully satisfy the observations, and none of them can be properly tested without another signal to study. Maybe there is a natural phenomenon we have not yet identified, something rare, something that requires precise conditions to occur, something that happens once in a generation or once in a century in any given region of space. We cannot rule this out. Maybe there was an equipment malfunction that produced exactly the right pattern. Unlikely, but not impossible. We cannot rule this out either. Maybe something was genuinely trying to communicate. Maybe the signal was a beacon, or a transmission, or the radio equivalent of a lighthouse. Maybe whatever sent it stopped transmitting. Maybe it only broadcasts occasionally, and we happened to catch a brief window. We cannot rule this out. We cannot rule anything out. That is the problem. That is the frustration. That is what happens when you have only one observation. As of 2025, it remains unexplained. The signal sits in archives. The question sits in our minds, and the universe offers no clarification. But here is something worth considering. The wow signal is frustrating precisely because we cannot study it further. We have one data point, and one data point is not enough to draw conclusions. What happens when we do have multiple observations? What happens when a mystery repeats itself, when we can watch it again and again, when we can gather data from dozens of separate events? Surely that would be easier. Surely repetition would give us the answers we seek. You might think so, but the universe has other ideas, because there are phenomena out there that repeat reliably, signals that return over and over, events we have observed hundreds of times with instruments far more powerful than Big Ear ever was, and we still do not understand them. Sometimes more data just means more questions. Let me tell you about something that broke the rules of what a star should do. In 2011, the Kepler Space Telescope was doing what it did best, staring at the same patch of sky, watching thousands of stars at once, measuring their brightness with extraordinary precision. Kepler was designed to find planets. The technique was simple. When a planet passes in front of its star, it blocks a tiny fraction of the light. Kepler could detect that dip. The math is straightforward. When Earth passes in front of our Sun, as seen from some distant vantage point, it blocks about 1/100% of the sunlight, almost nothing, a speck crossing a spotlight. When Jupiter makes the same crossing, the largest planet in our solar system, it blocks about 1%, still not much. A modest interruption. This is what normal looks like. This is the range we expect. Tiny dimming events that repeat at regular intervals as planets complete their orbits. Predictable, mathematical, clean. Then, Kepler found a star that refused to cooperate. The star sits 1,460 light-years away in the constellation Cygnus. Its catalogue designation is KIC 8462852. Nobody calls it that anymore. Astronomer Tabitha Boyajian led the team that analyzed the data. The star now carries her name, Tabby's star. In 2011, this star dimmed by 15%. Stop and consider what that means. Earth blocks 1/100%. Jupiter blocks 1%. This star dimmed by 15%. That is not a planet. That is not anything we have a name for. If something solid was passing in front of this star, it would need to be enormous, larger than the star itself, larger than physics says a planet can be. Then, in 2013, it happened again. The star dimmed by 22%. Imagine a fly crossing a spotlight. That is Jupiter. A tiny dark speck moving across the beam. The light barely flickers. Now imagine a beach ball blocking half that beam. That is what we saw at Tabby's star. The scale is completely different. The comparison breaks down. Nothing in our catalogue of celestial objects should cause this. And here is what made it stranger. The dimming did not repeat at predictable intervals. Planets orbit their stars like clockwork. The same dip happens at the same interval, over and over. That regularity is how we confirm that something is really there. Tabby's star showed no such pattern. The dimming events came randomly. They lasted different amounts of time. They blocked different amounts of light. Whatever was causing this did not follow an orbital path we could track. Something was blocking the light of this star. Something massive. Something irregular. Something that defied every natural explanation astronomers could offer. This is when the conversation took an unusual turn. In 1960, physicist Freeman Dyson proposed an idea. He was thinking about what an advanced civilization might do once it outgrew its home planet. Stars produce enormous amounts of energy. Most of that energy radiates out into empty space, wasted. What if a civilization wanted to capture that energy? Dyson did not suggest building a solid shell around a star. That would be structurally impossible. The mass required would be absurd. The engineering challenges insurmountable. Instead, he proposed something different. A swarm. Millions of individual structures orbiting a star. Solar collectors. Energy harvesting satellites. Each one relatively small. Together, forming a cloud that partially surrounds the star. Picture a cloud of solar panels drifting around a sun. Some panels pass in front of the star, blocking light. Others drift away. The arrangement constantly shifts. The shadows cast by this swarm would be irregular, unpredictable. They would block varying amounts of light at random intervals. That is exactly what we saw at Tabby's star. The alien megastructure hypothesis was not fringe speculation. It was not proposed by outsiders looking for attention. Mainstream astronomers considered it seriously. Papers were published. Conferences held discussions. The reason was simple. Every natural explanation kept failing. Comets breaking apart could not account for the scale. Planetary debris rings could not explain the irregularity. Dust clouds orbiting the star would create predictable patterns. Nothing fit. The scientists were not claiming it definitely was aliens. They were saying they could not rule it out. They had examined every conventional possibility. Each one fell short. Intellectual honesty required keeping all options on the table, even uncomfortable ones. This is how science is supposed to work. You follow the evidence, even when it leads somewhere strange. Then came 2017, a worldwide campaign of observations focused on Tabby's star. Astronomers watched it dim in real time. They measured the light across different wavelengths, and they noticed something. The dimming was more pronounced in blue light than in red light. This matters enormously. A solid object blocks all wavelengths equally. If something opaque passed in front of the star, blue and red light would disappear in the same proportions. That is not what happened. Blue light was blocked more than red light. This pattern suggests dust, tiny particles scattering shorter wavelengths more than longer ones. Dust, not a megastructure, something natural after all. But the mystery did not end there, because dust creates its own problems. A dust cloud large enough to block 22% of a star's light would be visible. We would detect its infrared glow. We would see evidence of collisions that created all that debris. We would find some trace of its origin. We see none of these things. The dust explanation tells us what is doing the blocking. It does not tell us where that dust came from. It does not explain why so much of it exists. It does not account for how a cloud this massive could form and persist around a star, without other signatures we can detect. One mystery replaced by another. We traded the question of what for the question of why. The shape of our ignorance changed. The ignorance itself remained. Tabby's star continues to dim irregularly. Astronomers continue to watch. Each new observation adds data to our records. Each new dimming event deepens the puzzle. We know more than we did in 2011. We understand less than we thought we would by now. This is the texture of cosmic discovery in our age. Our telescopes grow sharper. Our instruments grow more sensitive. We peer deeper into the darkness and see things that earlier generations could never have detected. We find answers to old questions, and we find new questions that make the old ones look simple. The sky above Cygnus holds a star that behaves like nothing else we have catalogued. Something obscures its light in ways that challenge our models. Natural processes may explain it. Exotic possibilities remain on the table. The truth hovers just beyond our current understanding, visible enough to tantalize, distant enough to frustrate. This is what happens when we look closely at the universe. The closer we look, the stranger it becomes. The more precisely we measure, the more anomalies we find. Every instrument we build, every telescope we launch, every survey we conduct reveals things that should not quite fit our expectations. The universe does not conform to what we find convenient. It simply exists, vast and strange, indifferent to our categories and models. We draw maps of what we understand. Then we find something like Tabby's star, and we realize our maps have edges. Beyond those edges, the territory grows wild. And this star, peculiar as it is, represents only one kind of strangeness: light being blocked by something we cannot explain. That mystery concerns itself with objects, with dust, with things that exist in space and cast shadows. There are other mysteries that concern themselves with space itself, with the fabric of the cosmos, with regions so vast and so empty that they challenge our understanding of how the universe is structured. Because if Tabby's star asks what is blocking the light, these other anomalies ask a different question entirely. They ask why there is nothing there at all, the emptiness, the absence, the places where galaxies should be but aren't. Those mysteries concern themselves with what isn't there. But there's another kind of strangeness, the kind where something is there, something enormous, something we've never seen before, something that was always present, hanging in the sky, waiting for us to build the instruments capable of detecting it. In 2019, astronomer Ray Norris and his team were using the Australian Square Kilometre Array Pathfinder, ASCAPI. It's a radio telescope designed to survey the sky in ways no instrument had managed before. The team was mapping radio emissions across vast stretches of space, routine work, cataloguing known objects, building a more detailed picture of the radio universe. Then they found circles, perfect circles, massive rings of radio emission, crisp and distinct against the background of space. Each one had a galaxy sitting at its center, not just any galaxy, usually an elliptical galaxy, old, dead, full of ancient stars. Norris and his colleagues checked their data, checked it again, looked for errors, looked for artifacts from the telescope, looked for anything that might explain what they were seeing. They found nothing wrong with their instruments. The circles were real. They called them odd radio circles, ORCs. The name captures the confusion perfectly. These objects don't fit into any category astronomers had established. They aren't supernova remnants. Those are too small by orders of magnitude. They aren't planetary nebulae. Same problem. They aren't the radio lobes that spray out from active black holes at the centers of galaxies. Many of these ORCs don't have active black holes. The circles just exist, and their scale defies intuition. Each ORC spans hundreds of thousands of light years at minimum. Some stretch over 1 million light years across. That's roughly 10 times the diameter of our entire Milky Way galaxy. Picture this. You walk into your backyard one morning and discover footprints pressed into the dirt, except these footprints aren't measured in inches. They're the size of a football stadium. You can barely comprehend what creature could have made them. You question whether your eyes are working correctly. That's the feeling astronomers had when they first measured these rings. As of 2025, about a dozen have been found. A dozen perfect circles scattered across the sky, each one surrounding a distant galaxy, each one emitting radio waves at frequencies we can now detect. Here's the thing. We genuinely don't know what creates these. We've ruled out supernova remnants because those are far too small. A supernova blast wave might expand for thousands of years, but it never produces anything approaching this scale. Not even close. We've ruled out planetary nebulae for the same reason. When a star sheds its outer layers at the end of its life, the resulting shell of gas reaches perhaps a few light years across. ORCs are 100,000 times larger. We've ruled out radio galaxy lobes because many ORCs don't have active black holes feeding jets of material into space. No engine to power such structures. Every explanation we've tried doesn't fit. That's not a failure of science. That's science working exactly as it should. You observe something. You form hypotheses. You test them against the data. When every hypothesis fails, you've learned something valuable. You've learned that your existing categories are incomplete, that the universe contains phenomena your models never anticipated. The leading theories now involve some kind of massive outburst from the central galaxy, perhaps a merger event billions of years ago that sent shockwaves rippling outward through intergalactic space. Perhaps something even more exotic, but these remain speculations, not explanations. The data doesn't yet support a definitive answer. What strikes me most isn't the mystery itself, it's when that mystery began. ORCs were always there. They didn't suddenly appear in 2019. They've been hanging in the sky for who knows how long. Millions of years, billions, possibly. Ancient structures surrounding ancient galaxies, radiating at frequencies human beings had no way to perceive until we constructed the right equipment. The universe didn't change. Our eyes got better. ASCAP can survey the radio sky with sensitivity and resolution that previous instruments couldn't match. It sees what older telescopes missed, not because older telescopes were flawed, but because the technology simply didn't exist to capture these faint, diffuse radio emissions spread across such enormous scales. Think about what that implies. Every time we build a better telescope, we don't just get sharper images of things we already knew about. We find new categories of objects, new phenomena, new questions we hadn't thought to ask because we didn't know there was anything there to question. Tabby's star was invisible to naked-eye astronomers for all of human history. Then we launched Kepler, and suddenly we had a mystery. ORCs were invisible to radio astronomers for decades. Then ASCAP came online, and we had another. The pattern repeats throughout the history of astronomy. Galileo pointed his telescope at Jupiter and found moons no one knew existed. Hubble showed us galaxies beyond the Milky Way. The James Webb Space Telescope reveals structures at the edge of the observable universe that earlier instruments showed as smudges, if they showed anything at all. Better tools don't solve mysteries. They reveal new ones. Every advance in technology expands the boundary of what we can perceive, and at every boundary, we find things that don't match our expectations, things that force us to revise our models, extend our categories, humble our assumptions. ORCs sit at that boundary right now, circles that shouldn't exist, structures that span cosmic distances without fitting any known template, objects that waited patiently in the darkness while human civilization rose and fell and rose again, while we invented radio and built our first crude receivers and slowly improved them over generations until finally, in 2019, someone looked at the data and saw perfect rings where no rings were supposed to be. A dozen so far, probably more waiting to be catalogued as surveys continue, perhaps many more, scattered across the universe in configurations we haven't yet mapped. And here's what keeps astronomers awake at night. If ORCs were hiding in plain sight all along, what else is out there? What other phenomena exist at scales and frequencies we haven't yet learned to detect? What will the next generation of instruments reveal that makes our current mysteries look simple? The circles surround galaxies, but there are structures far larger than galaxies, structures that string galaxies together like beads on cosmic filaments, structures so vast they strain the limits of what our models say should be possible. And some of those structures have recently been found to exceed those limits entirely, something worth stepping back to consider. All these mysteries we've been discussing, the strange signals, the impossible dimming, the perfect circles that shouldn't exist, they share something in common. They were invisible to every generation of humans who came before us. Not because ancient astronomers weren't clever, not because they lacked curiosity or dedication. They simply didn't have the right eyes. In 1609, a man in Italy pointed a tube with curved glass at the night sky. That moment changed everything. For the first time in the history of life on Earth, a creature could see beyond what evolution had given it. Galileo didn't discover the cosmos that night. He discovered that there was more cosmos to discover. That was 400 years ago. 4 centuries of serious astronomical observation. 400 trips around the sun while we've been paying attention, building instruments, writing down what we see. 400 years sounds like a long time. Your great-great-great-grandmother couldn't have imagined the telescopes we have today. Empires have risen and crumbled in 400 years. Languages have been born and died. It feels like a substantial window of observation. It isn't. The universe is 13.8 billion years old. 400 years out of 13.8 billion. Do the math and you get something humbling. 0.00003%. That's our window. That's how long we've been watching. Consider what that means. Studying the ocean for 2 seconds and claiming to understand the tides. Listening to a symphony for a single note and writing the music review. Reading one word of a novel and summarizing the plot. That's us. That's the sum total of human astronomical observation compared to cosmic history. Every confident statement we've ever made about the universe, every model, every theory, every law we've written down, all of it rests on observations taken during an almost infinitely small sliver of time. We've barely begun to look. The humility this demands is staggering. We build our physics from what we can see, and what we can see depends entirely on what we've built to see it with. Every generation looks up with instruments their parents couldn't have dreamed of, and every generation finds something their parents never knew to look for. The Kepler Space Telescope launched in 2009. Its mission was specific. Stare at one patch of sky. Don't look away. Watch 150,000 stars simultaneously and measure their brightness over and over and over again for years. From the ground, we can't do this. Our atmosphere shimmers and blurs. Clouds drift across our view. The sun rises and forces us to stop. Day interrupts night. Weather interrupts observation. Gravity tugs at our instruments. Kepler floated above all of that, patient, unwavering, catching dips in starlight that lasted hours, detecting fluctuations of 1/100%, variations so subtle that no human eye, no matter how keen, could have noticed them. This is how we found Tabby's star, not through brilliance or insight or a lucky guess, through mechanical persistence, through a machine that could watch without blinking while we slept and worked and lived our brief lives below. The Australian Square Kilometre Array Pathfinder works differently but pursues the same philosophy. 36 dish antennas spread across the Australian outback, all working together as a single instrument. Each dish listens to the radio sky. Combined, they survey vast stretches of space with sensitivity that previous radio telescopes couldn't approach. When those dishes found the first odd radio circles, they weren't looking for them. Nobody was. The circles revealed themselves because the instrument was good enough to see them. They'd been hanging in the sky the whole time, waiting, patient as the void. The James Webb Space Telescope now peers into infrared wavelengths deeper than any instrument before it. Light that our eyes can't perceive. Light that passes through dust clouds which block visible wavelengths. Light stretched by the expansion of space itself, shifted red and then redder still until it slips out of the visible spectrum entirely. Webb sees through cosmic curtains that blinded every previous telescope. Behind those curtains, galaxies we thought we understood look different than expected. Structures appear where models predicted emptiness. The early universe grows stranger the clearer our view becomes. And we're not done building. In the Atacama Desert of Chile, construction continues on the extremely large telescope. Its primary mirror will span 39 meters across. For comparison, the largest optical telescope currently operating has a mirror of about 10 meters. This new instrument will gather more light than any telescope in human history. When it opens its eye to the sky, It will see things we cannot predict, not because we lack imagination, but because imagination works from what we already know. The telescope will show us what we don't know to imagine. This is the pattern. Galileo saw moons around Jupiter that no philosopher had predicted. Later generations found entire galaxies beyond our own. The Hubble Space Telescope revealed that the expansion of the universe is accelerating, a discovery so unexpected it won a Nobel Prize. We keep building bigger eyes. The universe keeps showing us more. There's something both thrilling and deeply unsettling about this. Our models aren't wrong because we made mistakes. They're incomplete because we built them from incomplete data. And the data will always be incomplete because we will always be building the next telescope. Think about what this implies for everything we've discussed. The strange signals, the impossible objects, the structures too large for our equations to permit. These aren't bugs in the cosmic software. They're features we couldn't see until our instruments improved. How many more anomalies are out there right now, waiting for the next generation of telescopes? How many categories of objects exist that we haven't named because we haven't detected them yet? How many rules will we need to rewrite when the extremely large telescope begins its survey? We are living in a golden age of discovery, not because the universe decided to become strange in our lifetime, because our tools finally became good enough to notice what was always there. This golden age has a character different from previous eras of discovery. Earlier, astronomers found new objects one at a time. A comet here, a planet there, a nova that blazed and faded. Each discovery fit into the existing framework or gently extended it. The discoveries piling up now don't gently extend anything. They challenge foundations. They suggest that our understanding, built so carefully over 4 centuries, may need substantial revision. The framework itself feels less stable than it did a generation ago. And the telescopes under construction will make current instruments look primitive. The data they'll return will dwarf what we've collected so far. The anomalies they'll reveal will make today's mysteries seem quaint. 400 years of watching, 0.00003% of cosmic history. Every law of physics we've written came from that vanishingly small sample. We are certain of so much. We should perhaps be certain of far less. The next instruments are coming. The next impossible objects are waiting to be found. And somewhere out there, phenomena we haven't named yet are doing things our models say cannot happen. Let me tell you about something that shouldn't exist. Actually, 2 things. Both of them so large, they break the rules we've spent decades building. Both of them discovered by the same astronomer. Both of them sitting in the exact same region of sky. Before I explain what she found, you need to understand the rules she broke. Cosmologists operate on a fundamental assumption. They call it the cosmological principle. The idea is simple. At large enough scales, the universe looks the same in every direction. Not perfectly identical, but statistically similar. Galaxies cluster in some places and thin out in others. But if you zoom out far enough, everything averages out. The universe becomes smooth. Think of it like a perfectly shuffled deck of cards. Flip any random sequence of 10 cards, and you'll see different combinations. But flip 1,000 cards, 10,000, 1,000,000. The proportions start to balance. You get roughly the same mix of hearts, spades, diamonds, clubs. At large enough samples, randomness becomes uniformity. The cosmological principle says the universe works the same way. At sufficiently enormous scales, no region should look dramatically different from any other. No walls that span too far. No structures that grew too large. Everything should blend into cosmic sameness. This principle isn't just philosophical, it's mathematical. Gravity moves at a finite speed. The universe has a finite age. Combine these 2 facts and you get a hard limit, a cosmic speed limit for how big things can grow. That limit is about 1.2 billion light years. Nothing larger should exist, not because we haven't found it yet, because there hasn't been enough time since the universe began for anything bigger to form. Gravity simply cannot pull matter together across distances greater than 1.2 billion light years. The math forbids it. In 2021, Alexia Lopez of the University of Central Lancashire found something the math forbids. She was studying distant quasars. the brilliant cores of active galaxies. These quasars serve as cosmic landmarks, letting astronomers map the three-dimensional structure of the universe. Lopez noticed something strange in her data, a pattern, an arc. When she traced it, the arc stretched 3.3 billion light-years across. That's almost 3 times the theoretical maximum. The structure she discovered was so large it couldn't have formed in the time the universe has existed. Imagine you're an architect reviewing blueprints for a city. Your engineering says rooms can only be as big as houses. The materials, the physics, the load-bearing limits all point to the same constraint. Then someone shows you aerial photographs of a single wall that spans an entire continent. Your blueprints are either wrong or the photographs are lying. Lopez checked her data. She ran statistical tests. The probability that this arc was just a random arrangement of galaxies, a coincidence that looked like a pattern but wasn't, came out to roughly 1 in 6,000. Not impossible, but highly improbable. She named it the Giant Arc. The observable universe stretches 93 billion light-years across. The Giant Arc occupies 3.3 billion of that. To be clear, this isn't like finding a slightly larger than expected mountain. This is finding a mountain that physics says cannot stand. But Lopez wasn't done. In 2024, her team announced another discovery, a different structure in their data. This one wasn't an arc, it was a ring, a colossal circle of galaxies spanning 1.3 billion light-years in diameter. They called it the Big Ring, 1.3 billion light-years, just barely over the theoretical limit, close enough to make you uncomfortable. Here's where the story gets stranger. Both structures sit approximately 9.2 billion light-years from Earth. Both occupy the same general region of the sky. The Giant Arc, 3 times too large to exist. The Big Ring, just barely impossible. Neighbors. Finding one structure that violated the cosmological principle was troubling. Finding 2 in the same cosmic neighborhood feels like a message. Consider what this means. Either this region of space is fundamentally different from everywhere else, or our understanding of how structures form needs revision, or we're looking at the universe's most extraordinary coincidence. None of these options are comfortable. The discovery doesn't mean the Big Bang Theory is wrong. It doesn't overturn everything we know about cosmic evolution, but it does suggest that our models of structure formation, the equations we use to predict how galaxies cluster and walls form and voids empty, might need adjustment. We thought we understood the rules. The universe is telling us our understanding is incomplete. This matters because the cosmological principle isn't just an academic abstraction. It's the foundation we build everything else on. Our measurements of cosmic expansion, our estimates of the universe's age, our maps of the large-scale structure, all of these rely on the assumption that the universe is fundamentally uniform. If that assumption is wrong, we don't know what else might need recalculating. Lopez and her team are careful not to overstate their findings. Science requires confirmation. Other researchers need to verify the structures using different methods. The statistical analyses need independent replication. These are the checks that separate genuine discoveries from measurement artifacts. But the initial data is compelling. 2 impossible structures, same region, same distance, same team, looking at the same patch of sky and finding the same violation twice. The universe seems to be saying something. We just don't speak the language yet. There's a kind of vertigo that comes from discoveries like this. We build our models carefully. We test them against observations. They work beautifully for decades. Then something appears that the models say shouldn't be there. The structures are real. The light from those distant quasars traveled 9 billion years to reach us. The patterns Lopez found are embedded in data collected by instruments specifically designed to map the cosmos. This isn't a telescope glitch or a computer error. These are walls too long and rings too wide, hanging in the void, defying the equations we wrote to describe them. What else might we find when we look more carefully? What other rules might be incomplete? The cosmological principle promised us uniformity, a universe that, at the grandest scales, looked the same everywhere. No special places, no preferred directions, just endless cosmic sameness stretching in every direction. But sameness might be an illusion we invented because we hadn't looked closely enough. The Giant Arc and the Big Ring are not the only challenges to uniformity. There are other places in the cosmos where the expected patterns break down, places where the distribution of matter looks nothing like our models predict. One of those places is almost completely empty. Almost completely empty. That phrase barely captures it. The Boötes void stretches 330 million light-years across. That's more than 3,000 times the diameter of our own galaxy. If you could somehow travel from one side to the other at the speed of light, the journey would take longer than any civilization in human history has existed, longer than mammals have walked the Earth, longer than complex life has existed anywhere. A region this size, based on the average density of matter in the universe, should contain about 2,000 galaxies, spirals and ellipticals and irregulars, all spinning and colliding and evolving together. A cosmic neighborhood filled with billions of stars, trillions of planets, countless possibilities for light and life. The Boötes void contains roughly 60. Robert Kirshner discovered this emptiness in 1981. His team was mapping the distribution of galaxies in the northern sky, cataloging their positions and distances like cartographers charting unknown territory. What they found was territory with almost nothing to chart, a hole in the cosmos so large it took their breath away. Picture a neighborhood. Houses line the streets. Families live their lives. Children grow up surrounded by neighbors. There are interactions and conversations and the constant presence of others. A typical galaxy exists in this kind of environment. Other galaxies drift nearby. Gravity pulls them into slow dances that last billions of years. They exchange gas and stars. They collide and merge and transform each other. Being a galaxy in the Boötes void is like being the only house in a neighborhood where every other lot sits empty for 1,000 miles in every direction. Your nearest neighbor might be millions of light years away. You can't see them. You can't interact with them. Their gravity doesn't touch you. You exist in perfect, profound isolation. Think about what that means for the galaxies trapped inside. Most galaxies grow through violence. Collisions strip away gas. Mergers trigger bursts of star formation. Gravitational harassment from passing neighbors stirs up their cores and reshapes their structures. This constant interaction is how galaxies evolve. It's the cosmic equivalent of growing up in a community shaped by every encounter. Galaxies in the void experience none of this. They evolve without gravitational harassment. Like a child growing up without ever meeting another person, they develop in complete isolation, shaped only by their own internal processes. No collisions to trigger new stars. No mergers to transform their shapes. No gravitational tides pulling at their edges. These isolated galaxies are natural experiments, the universe set up without intending to. They show us what happens when evolution proceeds without external influence. They grow differently, more slowly, more quietly. This is the part that gets me. Think about it. If you're a galaxy in the Boötes void, you're alone. Not lonely in some poetic sense, but truly, physically isolated. The nearest gravitational neighbor might be so far away that light from them takes millions of years to reach you. You're evolving in silence, without the collisions and mergers that shaped most galaxies. You're a natural experiment the universe set up, testing what happens when a galaxy grows up completely alone. I find something almost melancholy in that. All those stars, all those worlds, all that potential for life and complexity, developing in complete cosmic solitude. If intelligent beings exist on a planet orbiting a star in one of those 60 galaxies, their night sky is almost empty. No nearby galaxies to wonder about, no cosmic neighbors to dream of visiting, just darkness stretching in every direction, interrupted only by the faint smudges of impossibly distant light. The loneliest place in the universe might actually be a place you could call home. Here's where the story becomes even stranger. This vast emptiness, this 330 million light-year expanse of almost nothing, traces back to something smaller than an atom. The cosmic microwave background formed about 380,000 years after the Big Bang. That ancient light carries a record of the early universe. Encoded in its subtle variations are the seeds of everything we see today. Tiny fluctuations in density, regions where matter was packed slightly more or slightly less tightly than average. These fluctuations were quantum in origin, microscopic ripples in the fabric of reality, smaller than the smallest particle we can detect, random variations generated by the strange rules that govern physics at the smallest scales. During cosmic inflation, the universe expanded faster than light. These quantum fluctuations stretched with it. What started as subatomic ripples became cosmic scale variations. Regions that were slightly more dense than average had more gravity. They pulled in more matter. Over billions of years, they became galaxies and clusters and the great walls of the cosmic web. Regions that were slightly less dense had less gravity. Matter flowed away from them. They expanded faster than their surroundings. Over billions of years, they became the voids. The Boötes void started as a tiny quantum fluctuation, a microscopic ripple in the quantum foam of space-time, something so small no instrument could ever measure it directly. And over 13 billion years, that nothing became this nothing. That microscopic emptiness became 330 million light-years of cosmic isolation. It's like a single misplaced stitch in a sweater, eventually becoming a hole you could fit your fist through. The smallest things can have the largest consequences given enough time, and the universe has had plenty of time. Scale collapses in both directions here. The incomprehensibly vast traces back to the incomprehensibly small. The void that dwarfs 3,000 Milky Ways began as something smaller than the nucleus of an atom. Every photon that crosses that emptiness, every lonely star that burns in those 60 galaxies, every world that might orbit in that cosmic wilderness, all of it exists because of a quantum tremor at the birth of time. The void remains one of the largest known empty regions in the universe. But it's not unique. Other voids scatter throughout the cosmos, each one tracing back to its own primordial fluctuation. The universe is textured this way. Dense regions where matter gathered, empty regions where matter fled, a cosmic web of filaments and walls surrounding bubbles of almost nothing. The Boötes void just happens to be one of the largest bubbles we've found, a monument to emptiness, a cathedral of absence built by quantum chance. I sometimes wonder what those 60 galaxies would look like to us if we could visit. Galaxies that never experienced a major merger. Stars that formed without the violent triggers of collision. Planetary systems that evolved without gravitational disruption from passing neighbors. Would life there be different? Would intelligence develop differently in a universe that seemed almost empty? What would beings from such a place think when they finally built telescopes powerful enough to see beyond their isolation, when they finally glimpsed the crowded cosmos beyond their void? Maybe they would feel the way we feel when we contemplate their loneliness. A strange mixture of sadness and wonder, the recognition that the universe contains places so different from our own that we can barely imagine existing there. The early universe left other marks besides the voids. Imprints in that ancient light that formed 380,000 years after everything began. Some of those marks are even harder to explain than the emptiness we've been dwelling in. The early universe left other marks besides the voids. Imprints stamped into the oldest light we can see, and one of those marks looks almost like a bruise. 380,000 years after the Big Bang, something remarkable happened. The universe finally cooled enough for light to travel freely. Before that moment, everything was so hot and dense that photons couldn't move more than a tiny distance before colliding with particles. The cosmos was opaque, a fog of fire filling everything. Then the temperature dropped below a critical threshold. Electrons combined with nuclei to form neutral atoms. And suddenly, for the first time, light could travel unimpeded across space. That light is still traveling. We call it the cosmic microwave background. It's everywhere, filling the universe like an ancient glow. The temperature of this light is 2.725 Kelvin. That's less than 3 degrees above absolute zero, almost unimaginably cold, and almost perfectly uniform in every direction we look. The uniformity is what matters here. Temperature variations across this ancient light are normally 1 part in 100,000. Picture this. Imagine measuring the height of every single person on Earth, all 8 billion of us. and finding that everyone varies by less than the thickness of a single human hair. That's the level of uniformity we're talking about. The early universe was astonishingly smooth, which makes any exception stand out. In 2004, scientists mapping this ancient light noticed something troubling. A spot in the southern sky, cooler than it should be, bigger than it should be, and statistically improbable in ways that still cause discomfort. The cold spot spans about 10 degrees across the sky. That doesn't sound like much until you compare it to something familiar. The full moon, as seen from Earth, takes up about half a degree. This cold region is 50 times larger than that apparent size. Imagine noticing a bruise the size of your entire torso. You can't ignore something that prominent. It demands explanation. The temperature difference itself is tiny in absolute terms. The cold spot is 70 millionths of a degree cooler than the surrounding cosmic background. That seems almost negligible. But in a sea of such extraordinary uniformity, even this whisper of difference screams for attention. It's like perfect silence broken by a single soft note. The note itself might be quiet, but in that context, you hear nothing else. The probability of such a spot appearing by random chance is roughly 2%. That sounds almost acceptable. Unlikely, but not impossible. Flip a coin 5 times and get 5 heads. It happens. But cosmology has a problem that ordinary statistics doesn't face. We only have one universe to examine. We can't run the experiment again. We can't compare our cosmic microwave background to 1,000 other universes to see if cold spots this size are normal. We have exactly one data point, and our one data point has this thing that shouldn't be there. Scientists looked for explanations. The most promising one involved something called the integrated Sachs-Wolf effect. The idea is elegant. If a massive void exists between us and that patch of ancient light, photons passing through would lose energy in a peculiar way. Picture a hiker entering a canyon. They climb down, losing potential energy as they descend. Then, they climb back up the other side, regaining that energy. In a static universe, the energy gained climbing out would equal the energy lost climbing in. The hiker would exit at the same elevation they started. But our universe isn't static, it's expanding, and that changes everything. The hiker enters the canyon and starts descending. But while they're walking, the canyon itself is stretching, getting wider. By the time they reach the bottom and start climbing out, the far wall is farther away than when they began. The canyon has grown, so when they finally exit, they've climbed up a longer slope than they climbed down. They've used more energy getting out than they gained going in. Photons crossing a supervoid experience something similar. They fall into the gravitational well of the void, gaining energy. But while they're crossing, the universe expands. The void stretches. By the time they climb out the other side, they've lost more energy than they gained. They arrive at our telescopes slightly cooler than they should be. The explanation works in principle. The problem is scale. For this effect to fully account for the cold spot's temperature deficit, the supervoid along that line of sight would need to be impossibly large. Larger than any void we've ever detected. Larger than theoretical models suggest should exist. Astronomers have looked. They found a void in that direction. But it's not big enough. Not nearly big enough. As of 2025, it remains unexplained, which brings us to a hypothesis that sounds like science fiction, but isn't. Some cosmologists have proposed that the cold spot could be evidence of something far stranger than a supervoid. They suggest it might be a scar, a bruise left over from a collision with another universe. In the moments after the Big Bang, during the violent early expansion of everything, our universe might have bumped against a neighboring universe. 2 bubbles of space-time pressing against each other. The collision would have left an imprint, a mark in the cosmic microwave background where energy transferred between the two. A region slightly different from everything around it. This isn't fringe speculation published in obscure corners of the internet. This hypothesis appears in peer-reviewed scientific papers. Serious researchers at serious institutions consider it a legitimate possibility, not confirmed, not even likely, but not dismissed either. The multiverse collision theory sits at the edge of what we can test. We can't visit the cold spot. We can't examine it up close. We can only measure its temperature from billions of light years away and wonder what made it different. Maybe it was a supervoid we haven't properly mapped yet. Maybe it was a statistical fluke in a universe of infinite possibilities. Maybe it was something we haven't thought of yet. Or maybe, just maybe, it was a collision with a universe we will never see, a neighbor we will never meet, another cosmos that brushed against ours for the briefest instant and left this mark as the only evidence it ever existed. The ancient light carries its secrets quietly. It glows at the edge of our instruments, just barely detectable, older than anything else we can observe. And somewhere in that glow, something left a bruise the size of 50 full moons. Something cooled a patch of the universe by 70 millionths of a degree. Something happened that our physics struggles to explain. The cosmos keeps records we're only beginning to read. Some of those records are written in the oldest light. Others are written in the strangest stars. Individual objects that break the rules in ways that seem almost personal. Let me tell you about something that breaks the rules of nuclear physics. 370 light-years away, in the constellation Centaurus, there's a star called Przybylski's star. Astronomers have been studying it since the 1960s, and for more than 60 years, it has refused to make sense. On the surface, it seems ordinary enough. It's an A-type star, about twice as massive as our Sun, 6 times brighter, the kind of star you might glance at in a catalogue and move on. But when astronomers first looked at its light through a spectrograph, they found something that shouldn't be there. Technetium. That single word sent ripples through the astrophysics community, because technetium is not supposed to exist in stars like this, not in measurable quantities, not after billions of years. Every element has a signature. When light passes through a star's atmosphere, certain wavelengths get absorbed by specific atoms. It's like a fingerprint. You can tell exactly what elements are present just by studying the light. And the fingerprint of Przybylski's star shows technetium, clear as day, unmistakable. Here's why that matters. Technetium is radioactive. Every isotope of it is unstable. The longest-lived version, technetium-98, has a half-life of 4.2 million years. That sounds like a long time. In human terms, it is. But in stellar terms, it's nothing. This star is several billion years old. Let me put that in perspective. Uranium-238 has a half-life of 4.5 billion years. That's why we still find uranium on Earth. The planet formed around 4.5 billion years ago, and uranium's half-life is roughly the same length. It's had time to decay, but not completely. Some remains. Technetium is different. A half-life of 4.2 million years means that after just a few tens of millions of years, essentially all of it should be gone. After 100 million years, you'd be searching for individual atoms. After a billion years, the idea of finding any becomes absurd. Yet this star has been shining for billions of years, and every time we look, the technetium is still there. Finding technetium in a billion-year-old star is like finding an ice cube that has somehow been sitting in boiling water for a century. Every law of physics says it should be gone. The heat should have melted it in seconds. Yet there it is, solid, cold, impossible, unchanged. So where is the technetium coming from? I want you to sit with that for a moment before I offer the hypotheses. This star has been shining for billions of years. Technetium-98 has a half-life of 4.2 million years. After just a few tens of millions of years, there should be nothing left. Yet every time we look, it's still there. How? Something is replenishing it. That's the only logical conclusion. The technetium we see today cannot be the technetium that formed when the star was born. It must be produced continuously. Something inside this star is creating short-lived radioactive elements right now, over and over, fast enough to maintain detectable levels despite constant decay. The mystery deepens when you look at what else is present. Przybylski's star doesn't just have technetium, it also has promethium, another element with no stable isotopes, and unusually high concentrations of rare earth elements, holmium, dysprosium, europium. The whole spectrum of its light is strange. Normal stars don't look like this. Even chemically peculiar stars don't look quite like this. One hypothesis has emerged that sounds almost too strange to take seriously, But the star is so bizarre that astronomers must consider it anyway. It involves something called the island of stability. Picture the periodic table. The heavier the element, the more protons in its nucleus. And generally, the more protons you pack together, the more unstable the atom becomes. The heaviest elements we've created in laboratories exist for fractions of a second before falling apart. But theoretical physics predicts something unusual. If you could push far enough up the periodic table, beyond the elements we've synthesized, you might reach a region where atoms become stable again, a hidden mountain peak beyond a range of collapsing hills. If you could reach it, you might find elements that could persist for millions or even billions of years. Elements we haven't discovered, elements we haven't named. The hypothesis suggests that Przybylski's star might contain these super-heavy elements, and as they slowly decay, they could produce technetium and promethium as intermediate products. We wouldn't be seeing elements that survived from the star's birth. We'd be seeing the decay products of something even more exotic. We may be looking at evidence of elements that don't appear on any periodic table hanging in any classroom on Earth. Elements produced by processes we don't understand. Elements that form only under conditions we've never witnessed. As of 2025, this remains speculation. We cannot prove super-heavy elements exist in this star. We don't have the technology to detect them directly. We can only see the strange fingerprints they might leave behind. The impossible presence of elements that should have vanished eons ago. Other explanations have been proposed. Perhaps nuclear reactions in the star's outer layers produce technetium continuously. Perhaps magnetic field interactions create unusual conditions. Perhaps there's something about A-type stars we fundamentally misunderstand. None of these explanations fully satisfy. Each one raises its own problems. Each one requires conditions that seem unlikely. The star remains a puzzle. For more than 6 decades, astronomers have returned to Przybylski's star again and again. The technology improves. The measurements get more precise. And every time, the same impossible fingerprint appears. Technetium, still there, still defying explanation. It's a reminder that our understanding of stellar chemistry is incomplete. We think we know how elements form in stars. We think we know how they decay. We think we know what should and shouldn't exist. And then, a single star, 370 light-years away, quietly proves us wrong. The light from this star has been traveling toward us for nearly 4 centuries. When it left, Galileo had just turned his telescope toward the sky. By the time it reached our instruments, we had built spacecraft and split atoms and walked on the moon. And still, we cannot explain what we see. Some mysteries announce themselves with explosions and collisions. Others whisper. Przybylski's star whispers. It sits in the constellation Centaurus, burning steadily, unremarkably, containing elements that physics insists cannot be there. The universe keeps its strangest secrets in plain sight. Sometimes, the most profound discoveries aren't about what we find. They're about what we cannot explain. This star hasn't changed in 60 years of observation. Our theories haven't caught up. The gap between what we know and what we see remains stubbornly wide. Perhaps one day we'll detect super-heavy elements directly. Perhaps we'll find the island of stability and chart its shores. Perhaps the answer will turn out to be something no one has imagined yet. Until then, the ice cube sits in boiling water. The impossible persists. And somewhere in Centaurus, a star continues to break the rules. Not everything strange comes from within our galaxy. Sometimes, the truly alien arrives from somewhere else entirely. Objects that formed around distant suns, wandered through interstellar space, and happened to pass through our little corner of the cosmos. October 19th, 2017. A telescope in Hawaii captured something that had never been seen before. Not a new star, not a distant galaxy, something else entirely, something that didn't belong here. The Pan-STARRS Observatory was scanning the sky, cataloguing objects, doing its usual work, and in that data, astronomers found a visitor, an object moving through our solar system on a trajectory that could only mean one thing. It came from somewhere else, another star system, another part of the galaxy entirely. They named it Oumuamua. In Hawaiian, it means scout or messenger, the first confirmed interstellar object ever detected passing through our cosmic neighborhood, the first piece of another solar system we could actually observe. It approached from the direction of the constellation Lyra. It swung around our sun, and then it began its long journey back out into the dark. We had weeks to study it, just weeks. And in that brief window, it revealed itself to be one of the strangest things we've ever encountered. The shape was wrong. Astronomers measured its dimensions as best they could from the way its brightness changed as it tumbled through space. What they found was unlike any asteroid or comet in our solar system. Approximately 400 meters long, roughly 40 meters wide, a 10-to-1 ratio. Picture a pencil tumbling end over end through the void. That's the shape we're talking about. Not a rough potato like most asteroids, not a dirty snowball like most comets. A long, thin object spinning through space with proportions we had simply never seen before. Its surface was reddish. The color suggested organic compounds baked by cosmic radiation over millions of years of wandering between the stars. That part made sense. An object drifting through interstellar space for eons would accumulate that kind of weathering. But then came the first real puzzle. There was no coma. When a comet approaches the sun, the heat vaporizes ice on its surface. This creates a glowing cloud of gas and dust surrounding it. We call this the coma. It's what gives comets their fuzzy appearance. It's what creates their tails. Oumuamua had nothing. No cloud, no tail, no outgassing of any kind. The telescopes searched carefully. They found only the bare object itself, tumbling silently against the stars. Perhaps it wasn't a comet at all. Perhaps it was simply a very strange asteroid from a distant solar system. That explanation held for a while. Then the measurements got more precise, and everything changed. Oumuamua was accelerating, not in a way that gravity could explain. As it moved away from the sun, it was speeding up slightly more than the sun's gravitational pull alone could account for. Something was pushing it. For a comet, this would be normal. The jets of gas escaping from the surface act like tiny rockets, nudging the object in unpredictable directions. Astronomers call this non-gravitational acceleration. They see it all the time. But Oumuamua had no jets, no gas, no coma. Nothing visible was providing thrust. Imagine watching a car speed up on an empty highway. No visible engine, no exhaust, no sound. It simply accelerates, and you can see nothing causing it. Something is providing thrust, but you cannot identify what. That was Oumuamua, accelerating away from the sun with no apparent cause. In 2018, 2 Harvard astronomers published a paper that captured the world's attention. Evi Loeb and Shmuel Bialy suggested something remarkable. What if the object wasn't natural at all? What if Oumuamua was an artificial light sail pushed by the pressure of solar radiation? Light has momentum. When photons strike a surface, they transfer a tiny amount of force. For everyday objects, this force is negligible. But for something extremely thin and light, spread across a large area, solar radiation pressure could provide meaningful acceleration, a light sail, the kind of technology we've dreamed about for interstellar travel, the kind of technology an advanced civilization might use to explore the galaxy, or to send messages across the void. These weren't fringe theorists making this suggestion. This was Harvard's astronomy department, peer-reviewed research, a serious hypothesis put forward by serious scientists because the data was genuinely that strange. The scientific community pushed back. Many astronomers found natural explanations more plausible. Perhaps Oumuamua was made of pure hydrogen ice that sublimated invisibly. Perhaps its surface was composed of materials we simply couldn't detect. Perhaps the acceleration had some other cause we hadn't considered. The debate continues. We don't know the answer. We may never know, because Oumuamua is gone. It passed through our solar system in a matter of months. By the time we understood how strange it was already too far away to study further. Our telescopes lost sight of it as it sailed back into interstellar space. It's still out there now, somewhere in the dark between stars. carrying its secrets with it forever. We missed our chance. The first messenger from beyond, and it slipped through our fingers before we could understand it. Then, in 2019, something remarkable happened. A second interstellar object was discovered. An amateur astronomer named Gennady Borisov spotted a comet that was also on an interstellar trajectory. Another visitor from another star system. Scientists were excited. Perhaps this one would help explain Oumuamua. Perhaps interstellar objects were all strange in similar ways. Borisov was perfectly normal. A textbook comet. A bright, beautiful coma surrounding its nucleus. Predictable outgassing. Standard composition. It looked exactly like the comets we see in our own solar system. It behaved exactly as our models predicted. There was nothing unusual about it at all. This made Oumuamua stranger, not more normal. If interstellar objects are typically ordinary comets, then why was our first visitor so bizarre? Why the extreme shape? Why the missing coma? Why the unexplained acceleration? The universe sent us two messengers 2 years apart. One was completely familiar. The other was like nothing we had ever seen before or have seen since. Sit with that for a moment. Our first contact with material from another star system was an object that defied every expectation. That matched no known category. That behaved in ways we still cannot explain. And now it's gone. Traveling through the galaxy at over 50,000 miles per hour, getting farther away every second of every day. We'll never send a probe to catch it. We'll never get better images. We'll never sample its surface or analyze its composition. The questions it raised will remain questions. The mystery it presented will remain a mystery unless another one comes. Somewhere out there, drifting between the stars, there may be more objects like Oumuamua, billions of them perhaps, ejected from distant solar systems, wandering the galaxy for millions of years. Most will never pass close enough to any star for anyone to notice. But some might. Some might wander through our little corner of the cosmos. And this time, perhaps we'll be ready. Better telescopes, faster response times, maybe even spacecraft designed to intercept them. The messenger came and went. We heard only a few words of what it had to say. The rest is silence now, receding into the dark, carrying answers we desperately wanted to questions we barely knew how to ask. That's the nature of discovery sometimes. The universe shows you something extraordinary, gives you just enough information to know that everything you thought you understood might be incomplete, and then it takes the evidence away, leaving you with wonder and frustration in equal measure. Oumuamua is out there right now, tumbling through the void, growing colder and darker and more distant with every passing hour. Our first interstellar visitor, perhaps natural, perhaps not. Certainly unlike anything we've encountered before or since. The universe sends its messengers when it chooses. We can only watch and wonder and wait for the next one to arrive. There is a star in the constellation Libra that seems older than it should be. Its name is HD 140283. Astronomers call it the Methuselah star, after the biblical figure said to have lived 969 years. The star has earned that name. It drifts through our galaxy 190 light-years away, close enough that we can study it in extraordinary detail, close enough that we can measure its composition, track its motion, analyze the light it emits. And everything we learn about this star creates a problem we haven't solved. The Methuselah star is what astronomers call metal poor. In astronomy, any element heavier than hydrogen and helium is considered a metal. Iron, carbon, oxygen, all metals. The sun contains plenty of these heavier elements, forged in the cores of stars that lived and died before our solar system formed. This ancient star contains 250 times less iron than the sun. Almost none of the heavy elements that make up planets like Earth. Almost none of the cosmic debris that comes from stellar explosions. The Methuselah star is remarkably pure, hydrogen and helium, with barely anything else. That purity tells us something important. It tells us this star formed when the universe was very young, before generations of massive stars had exploded and scattered their heavier elements across space, before the raw materials for rocky planets existed in abundance. This star was born in an almost pristine cosmos. Astronomers calculate stellar ages through several methods. They examine how much hydrogen fuel a star has consumed. They measure its luminosity and surface temperature. They study its position on charts that map stellar evolution. They analyze that chemical composition, searching for clues about when and where the star formed. All these methods point toward the same conclusion for the Methuselah star. It is approximately 14 billion years old. The universe itself is 13.8 billion years old. We know this figure with remarkable precision. Multiple independent measurements agree. The cosmic microwave background, the expansion rate of space, the ages of the oldest known objects. Everything converges on that number. 13.8 billion years since the beginning of everything. The Methuselah star appears to be 200 million years older than everything. Consider what that means. This star seems to have existed before the universe did. That is, of course, impossible. Nothing can predate the beginning of time. Nothing can exist before existence itself began. And yet, here is a star, drifting peacefully through our galactic neighborhood, with a calculated age that extends past the boundary of creation. It's like finding a birth certificate dated before the hospital was built. Either the certificate is wrong, the hospital records are wrong, or something very strange happened. The scientific community has not dismissed this as simple measurement error. The numbers are too well established for casual dismissal. The Methuselah star has been studied extensively. Its age has been calculated and recalculated. The measurement techniques have been refined and improved. Each time, the answer comes back the same. Old. Impossibly old. The error bars provide some comfort, but not much. Scientific measurements include ranges of uncertainty. A star's age isn't calculated as a single precise number, but as a range of possibilities. The Methuselah star's error bars technically allow for ages just barely younger than the universe. That word technically is doing a lot of work in that sentence. The error bars overlap with the age of the universe by the thinnest margin. They touch at the edges, like two circles that just barely kiss. The star could be 13.7 billion years old. It could be 14.2. The range includes ages both possible and impossible. Astronomers find this deeply uncomfortable. Not wrong, exactly, but not cleanly resolved either. The numbers fit together too tightly. There's no breathing room between what should be true and what might not be. If the star formed from material scattered by the first generation of massive stars, there are limits to how old it can be. Those first stars needed time to form, burn through their fuel, and explode. The earliest second-generation stars could not have formed until roughly 300 million years after the Big Bang. That sets a maximum possible age around 13.5 billion years. The Methuselah star's calculated age exceeds even that limit. Perhaps our techniques for measuring stellar ages need refinement. Perhaps there are systematic errors we haven't identified. Perhaps the models we use to track stellar evolution are missing something. Each possibility suggests that our understanding is incomplete in some fundamental way, or perhaps our measurement of the universe's age needs adjustment. The 13.8 billion year figure comes from precise observations, but precision doesn't guarantee accuracy. There could be unknown factors affecting our calculations, dark energy behaving differently than we assume, expansion rates varying in ways we haven't detected. Either our stellar physics is slightly wrong, or our cosmology is slightly wrong. Those are the only options. Both are uncomfortable. As of 2025, it remains unexplained. There's something almost reassuring about that phrase by now. A familiar refrain in a universe that keeps presenting us with things that don't quite fit. The Methuselah star joins a growing list of cosmic puzzles that resist easy answers. The discomfort this creates in the astronomical community runs deep. Scientists are careful people. They don't enjoy publishing ages that approach or exceed the age of everything. They check their work. They question their assumptions. They invite colleagues to find the flaw in their reasoning. No one has found a satisfying resolution. The star continues to shine. It has outlasted empires and extinctions. It was ancient when Earth formed. It was old when the Milky Way was young. It carries within its spectrum the signature of a cosmos that barely had time to cool before this particular ball of hydrogen ignited. Perhaps the measurements will eventually converge on an age safely younger than the universe. Perhaps new techniques will resolve the tension. Perhaps we will look back on this puzzle and smile at how worried we were about numbers that turned out to be perfectly compatible. Or perhaps this star is telling us something we don't yet understand. A message written in fusion and time. A reminder that our models, however precise, are still approximations of a reality more complex than we imagined. The Methuselah star is not the only cosmic phenomenon that challenges our timeline. Throughout the universe, events occur with speeds and intensities that push against the boundaries of what we thought was possible. Let me tell you about something that happened in June of 2018, something that rewrote textbooks. Telescopes around the world detected a bright explosion in a distant galaxy, 200 million light-years away, far enough that the light left during the age of dinosaurs, close enough that our instruments could study it in extraordinary detail. The automated naming system designated it at 2018 Cow. The letters were random. That's just how the catalogue works. But the name stuck. Astronomers around the world now study the cow with completely straight faces. Sometimes science has a sense of humor, whether it means to or not. What made this explosion different wasn't just its brightness. Supernovae are bright. We've studied thousands of them. We thought we understood how stars die. Type Ia supernovae, Type II supernovae, hypernovae, pair instability supernovae. Astronomers had built a complete catalogue. Every possible way a massive star could end its life had been documented and explained. The physics were settled. The case was closed. The cow changed that. This explosion was somewhere between 10 and 100 times brighter than a typical supernova. Not 10% brighter, not twice as bright, up to 100 times. The numbers seemed wrong at first. Observers double-checked their instruments. They compared data from multiple telescopes. The measurements held. But brightness alone wasn't what shattered expectations. Speed was. A normal supernova takes weeks to reach its peak brightness. The star's outer layers expand and glow. Material spreads into space. The light rises gradually, crests, then fades over months. You can track the process like watching a slow-motion explosion. There's time to study each phase, time to understand what's happening. The cow peaked in days, not weeks, days. Then it faded in weeks instead of months. The entire event happened faster than it should have been possible. Picture a firework designed to burn for an hour. You light it expecting a slow, sustained display. Instead, it detonates in a single second. All that energy, all that light, compressed into a moment so brief you barely register what happened. The physics that should slow it down simply don't apply. That's what astronomers witnessed. A cosmic flashlight switched on, blazed with impossible intensity, then switched off again, brief and blinding. Temperatures reached tens of thousands of degrees. The spectrum revealed elements moving at tremendous speeds. Something was driving this explosion differently than any supernova model predicted. Within months, astronomers had a new category: fast blue optical transients, FBOTs. The name describes exactly what they are. Fast, because they rise and fall in days instead of weeks. Blue, because of their extreme temperatures. Optical, because we see them in visible light. Transient, because they come and go. The cow was the first well-documented member of this class, the first FBOT we caught early enough to study properly. But as astronomers started looking through older data, they found hints of similar events, brief flashes that hadn't fit any category, anomalies dismissed as instrument errors or overlooked entirely. The universe had been producing these explosions all along. We just hadn't known to look for them. Consider what this means. For decades, stellar death seemed like a solved problem. The equations worked. The observations matched. When a massive star ran out of fuel, we knew what would happen. Core collapse, shock wave, expansion, fade. The process varied depending on the star's mass and composition, but the basic framework applied everywhere. Textbooks printed the same diagrams year after year. Then, a single event in a distant galaxy proved that nature has ways of destroying stars we hadn't imagined. The catalogue wasn't complete. It might never be complete. As of 2025, we've found more FBOTs, Each one teaches us something new. Some seem to involve material falling onto a compact object, perhaps a black hole or neutron star formed in the explosion's core. The infalling matter releases energy at staggering rates. Other explanations suggest jets of material punching through the dying star's outer layers. The beam happens to point toward Earth, making it appear brighter than it otherwise would. No single theory explains all of them yet. The physics remains under construction. There's something humbling about watching this happen in real time. These discoveries aren't dusty artifacts from a previous era. They're happening now. Telescopes sweep the sky every night. Automated systems flag unusual brightness changes. Graduate students and established professors alike review alerts, trying to catch the next strange event before it fades. The cow itself is gone now. Its light has dimmed below detection. But it left behind a puzzle that keeps scientists working late into the night. What combination of mass, composition, and circumstance produces such violence? What happens in those final moments before a star tears itself apart in this new way? We don't fully know. That's the honest answer. The data suggests possibilities. Models narrow the options. But the complete picture remains just out of reach. This is how discovery works. You think the map is finished, every coastline charted, every mountain named. Then someone sails a little further and finds land where ocean should be. The map expands. The edges retreat. F-bots expanded our map of stellar death. Stars can die in ways we never predicted, ways that compress tremendous energy into impossibly short timescales, ways that produce light we can see across 200 million light-years of empty space. What else might be out there? What other categories don't exist yet because we haven't witnessed the right event at the right moment? The sky holds answers we haven't learned to ask for. Every night, light arrives from distant explosions. Some fit neatly into existing categories. Some, like the cow, refuse to comply. They sit outside our frameworks, demanding new physics, new models, new understanding. The catalogue of cosmic explosions continues to grow. Scientists add pages they didn't know were missing. And somewhere out there, right now, another star may be preparing to die in a way that will surprise us all over again. The surprises keep coming. And maybe that's the point. We've traveled a long way together, from a radio signal that rang out once in 1977 and never returned, through a star dimming by amounts that no planet could explain, past enormous circles of radio waves that span distances our telescopes couldn't measure until recently. We walked along a cosmic arc stretching across a third of the visible sky. We wandered through a ring of galaxies so large it defies the limits physics sets for how big things can grow. We stood at the edge of a void containing almost nothing, where emptiness stretches further than any distance you can imagine. We looked at the oldest light in existence and found a spot that was too cold, too large, too improbable. We visited a star burning with elements that should have vanished long before our sun was born. We watched an interstellar visitor pass through our neighborhood, tumbling with motion that made no sense, and then disappearing forever. We witnessed a star explode in a way no textbook predicted, and we met another star that might be older than everything else combined. 10 mysteries, 10 moments where reality refused to match our expectations. Here's what strikes me. These anomalies don't seem connected. A signal from a distant part of the galaxy has nothing obvious to do with a cold spot in the cosmic microwave background. An interstellar rock tumbling past the sun shares no apparent link with structures billions of light-years wide. An explosion 200 million light-years away and a star just a few hundred light-years from Earth seem to exist in completely different categories, different scales, different timescales, different branches of physics entirely. And yet, there is a pattern, not in the anomalies themselves, but in what they represent. Each one marks a place where our models stopped working. Each one is a boundary, a wall we built from our best understanding, only to find reality standing on the other side, waiting. The pattern isn't about radio signals, or stellar ages, or impossible structures. The pattern is about limits, our limits. Every field of science has moments like this, moments when the data says one thing and the theory says another, When observations pile up that don't fit the existing framework, when researchers look at each other and quietly acknowledge that something is wrong with the picture they've been painting. Those moments feel uncomfortable. They feel like failure, but they're not. They're the opposite of failure. They're the necessary first step towards something better. Consider what it means when a theory breaks. It means the universe has revealed something the theory didn't account for, something real, something that was always there, operating according to rules we hadn't discovered yet. The theory wasn't wrong in the way a lie is wrong. It was incomplete in the way all maps are incomplete. This has happened before, many times. Every major shift in how we understand the cosmos began with anomalies, with observations that didn't fit, with measurements that seemed impossible under the existing framework. The universe doesn't care about our comfort. That's not cruelty. It's just how things are. Reality has no obligation to match our expectations, no requirement to fit inside our equations. The cosmos existed for billions of years before we arrived, and it will continue long after we're gone. It operates according to its own rules, whether we've figured them out or not. Our job isn't to make the universe obey our theories. Our job is to listen when it tells us our theories need work. Think about the pattern we've seen, a signal that shouldn't exist under any natural explanation we've confirmed. A star dimming by amounts that demand objects larger than any planet, structures that exceed the theoretical maximum size, a void that challenges our models of cosmic evolution, a temperature variation that defies probability, elements that should have decayed away, a visitor that accelerated without visible cause, an explosion that created a new category, a star that appears to predate its own birthplace. These aren't scattered failures, they're systematic evidence. Evidence that our current understanding has edges, boundaries beyond which the familiar explanations stop working. Some of these anomalies may eventually be resolved. New data might arrive. Better instruments might reveal what we're missing. A clever insight might show how the existing physics actually does explain what we're seeing. But some of them may require something bigger, something more fundamental, a shift not just in our answers, but in the questions we ask. That possibility should excite us, not frighten us, because the moments when everything changes are the moments when we learn the most, when we take the biggest steps, when the map expands not by inches, but by entire continents. The anomalies we've discussed span almost the entire range of cosmic scales, from individual stars to the largest structures that exist, from events that happened recently to patterns imprinted when the universe was less than 400,000 years old. They touch nearly every branch of astrophysics, stellar evolution, cosmology, radio astronomy, transient detection, interstellar objects. The fact that mysteries appear across all these domains suggests something important. We're not dealing with small gaps in an otherwise complete picture. We're dealing with fundamental uncertainties about how the universe works at every level we can observe. That might sound discouraging. It's not. It's an invitation. These anomalies are open doors. Each one leads somewhere we haven't been. Each one offers the possibility that what we find on the other side will reshape what we thought we knew. Not all of them will deliver revolutions. Some might turn out to be measurement errors or statistical flukes or overlooked natural processes. But history suggests at least some of them are real. At least some of them point toward physics we haven't written down yet, toward relationships we haven't recognized, toward a universe stranger and richer than the one described in our current textbooks. The universe doesn't care about our comfort. It will continue producing signals we can't explain, stars that dim when they shouldn't, structures that exceed our limits, voids and cold spots and impossible elements and visitors from beyond. Our choice is whether to turn away or to lean in, to pretend the anomalies don't matter, or to recognize them for what they are: messengers, guides, proof that there is more to discover. The mysteries we've explored aren't failures of science. They're invitations to do better science, to ask sharper questions, to build better instruments, to imagine possibilities we haven't considered yet. Somewhere out there, right now, light is traveling toward us from events we don't yet have names for, from phenomena we haven't observed, from processes that will surprise us the way these 10 anomalies surprised the researchers who first encountered them. The cosmos keeps its secrets until we're ready to find them, and sometimes, even when we find them, we're not ready to understand them. Not yet. That's not a problem. That's the work. That's what it means to study a universe that has been here for nearly 14 billion years while we've been seriously looking for only a few centuries. We are early in this story. The beginning, really. And the strangest discoveries may still be waiting. This is what discovery looks like. Not neat answers arriving on schedule, but confusion first. Contradiction. The data says one thing, everything we know says another. It has always been this way. At the start of the 20th century, astronomers looked at the night sky and saw something eternal. Stars moved, yes. Comets came and went, but the universe itself was fixed, unchanging. It had always existed and would always exist. This wasn't a guess. It was the consensus, the settled science of the time. Then came the observations that didn't fit. Astronomer Vesto Slipher noticed that distant galaxies showed their light shifted toward the red end of the spectrum. This meant they were moving away from us. Not some of them, almost all of them. That was strange. If the universe was static and eternal, why would everything be racing away in every direction? Edwin Hubble took this further in 1929. He measured distances to dozens of galaxies and found something even stranger. The farther away a galaxy was, the faster it seemed to be receding. There was a relationship, a pattern. That pattern broke everything. If galaxies were flying apart now, they must have been closer together before. Go back far enough and everything would have been in the same place. The universe wasn't eternal. It had a beginning. This idea met resistance. Some astronomers spent decades trying to explain it away. They proposed that new matter appeared constantly in the gaps as space expanded, anything to preserve the eternal cosmos. But the observations won. The static universe died. What replaced it was a cosmos that had been born, that was expanding, that had a history. We call that history the Big Bang. Today, it's so familiar we forget that it came from anomaly, from observations that contradicted what everyone believed. The same pattern repeated in the 1960s. Radio astronomers scanning the sky found point-like sources that looked like stars. But when they measured the light from these objects, something was wrong. The redshift values were enormous. If those redshifts were real, these objects were billions of light years away. That meant they were unimaginably bright, brighter than entire galaxies, yet concentrated in a region smaller than our solar system. Astronomers called them quasi-stellar objects, quasars. They were impossible. Nothing we knew about stars, about fusion, about any physical process could explain that much energy from that smaller space. For years, quasars sat at the edge of understanding. Some proposed they weren't actually that far away. Maybe the redshift meant something different for these objects. Maybe our whole framework for measuring cosmic distances was flawed. The resolution came slowly. We learned that supermassive black holes exist at the centers of galaxies. Matter falling toward these black holes releases tremendous energy as it spirals inward. More energy than nuclear fusion. More energy than anything else in nature. Quasars weren't violations of physics. They were revelations. Windows into phenomena we hadn't imagined. Today, we use quasars as tools, cosmic lighthouses marking the distant universe. The anomaly became foundational knowledge. The mystery became a measuring stick. The third example is closer to our own time, close enough that many people alive today remember when it happened. In 1998, two teams of astronomers were studying distant supernovae, type Ia supernovae specifically. These stellar explosions have a special property. They all release roughly the same amount of light. This makes them cosmic rulers. If you know how bright something truly is and how bright it appears, you can calculate how far away it is. The teams expected to measure how much the universe's expansion was slowing down. Gravity should be pulling everything back together. The expansion should be breaking. The observations showed the opposite. Distant supernovae were dimmer than expected, not by much, but consistently. The universe's expansion wasn't slowing down, it was speeding up. This made no sense. Gravity pulls things together. There was no known force pushing the cosmos apart faster and faster over time, yet the data was clear. Multiple teams, independent measurements, the same result. What followed was a revolution. To explain the accelerating expansion, physicists proposed that empty space itself contains energy. Not particles, not radiation, just the vacuum, pushing outward. They named it dark energy, which is really another way of saying we have no idea what it is. Here is the part that deserves a moment of reflection. 68%. That's how much of the universe's total energy budget is dark energy. Not 10%, not some small correction factor, the majority of everything that exists. And we discovered this less than 30 years ago. Within living memory, we were completely unaware that most of the universe was made of something we cannot see, cannot detect directly, and cannot explain. It shapes the fate of everything. Whether the cosmos will expand forever or eventually slow and stop depends on this mysterious component. That knowledge came from anomaly, from observations that refused to match expectations, from supernovae that appeared slightly too dim for their distance. Think about that timeline. 4 centuries of telescopes, generations of astronomers building theories, and the dominant component of the universe remained hidden until 1998. The pattern is unmistakable. Static universe becomes expanding universe. Impossible quasars become black hole signatures. Decelerating expansion becomes accelerating expansion, driven by something we still don't understand. Each breakthrough started as contradiction. Each revolution began when someone measured something that shouldn't be there. As of 2025, dark energy remains unexplained. The refrain sounds different now. Not frustrated, not defeated, just honest about where we are. We know dark energy exists because we can see its effects. We know it dominates the universe's energy. We do not know what it is. We do not know why it has the value it has. We do not know if it changes over time. This is what anomaly looks like before it becomes understanding. The dimming star, the impossible structures, the empty void and cold spot, the strange elements and tumbling visitor, the explosions too bright and stars too old. Each one sits where dark energy sat in 1997, before the observations that changed everything, before the contradiction resolved into clarity. We cannot know which of today's mysteries will lead to the next rewriting of textbooks. Maybe several, maybe all of them, maybe none, and the revolution will come from something we haven't noticed yet. But history tells us that the confusion is not failure. The confusion is prelude. So where does that leave us? We've traveled through dimming stars and impossible structures, empty voids and cold spots, elements that shouldn't exist, and visitors from beyond our solar system, explosions too fast and stars too old. Every mystery we've explored shares something in common. They remain unsolved. And I think some people hear that and feel disappointed. There's a common belief about science, a misconception really, the idea that science is supposed to give us answers, that the goal is certainty, that if something remains unexplained, then science has somehow failed. We don't really know. That's the honest answer. And here's the thing, that's okay. That's actually normal in the history of science. The uncomfortable truth is that we've never had everything figured out, no matter how confident we felt at the time. The universe doesn't care about our theories. It doesn't care about our expectations. It simply is. Our job is to observe, to measure, to theorize, and to stay humble enough to admit when we're wrong. That last part matters more than we sometimes like to admit. There have been moments throughout history when scientists believed they were nearly finished, that the major work was done, that all that remained was filling in small details and adding decimal places to already known values. Before a certain patent clerk rewrote physics, many thought the framework was complete. Before we understood the cosmos had a beginning, scholars assumed it had always existed and always would. Each generation's confidence was eventually humbled by something unexpected. This keeps happening. It has happened so reliably that we should probably expect it to keep happening. The mysteries in this video exist at different stages. Some may be explained within the next few decades as telescopes improve and data accumulates. Some may require physics that hasn't been invented yet, concepts we cannot currently imagine. and some may never be fully resolved. We may simply lack the information needed to answer them. The evidence might have faded or traveled too far or changed in ways we cannot reconstruct. That uncertainty is not a flaw in the process. Think about what it actually means to confront something you cannot explain, to look at data that contradicts your best models, to measure something that, according to everything you know, should not be there. This is uncomfortable. It creates tension. It can feel like failure, but it isn't. The astronomers studying that dimming star in Cygnus are not frustrated by the lack of explanation. They are energized by it. The researchers examining strange elements in that peculiar star are not defeated. They are motivated. The teams mapping structures too large to exist are not giving up. They are paying closer attention. The mystery is the point. Every answered question in science started as an unanswered one. Every breakthrough began with confusion. Every elegant theory emerged from a period when the data made no sense. This is how the process works. You gather observations. You notice when they conflict with expectations. You sit with that conflict, sometimes for years, sometimes for generations. And eventually, if you're patient and honest, understanding emerges. Or it doesn't. And that's okay too. Some questions may outlive us. Some puzzles may never be completed. The cosmos is under no obligation to reveal itself on our schedule. We are small creatures on a small world, peering outward with instruments we invented only recently, trying to comprehend something vast and ancient and utterly indifferent to our desire for clarity. The privilege is in the looking. There's something almost sacred about honest uncertainty, about standing before the unknown and admitting you don't have the answer. It takes courage, in a way. It's easier to pretend you know. It's easier to fill the gaps with speculation or dismiss the anomaly as measurement error. But the scientists who advance understanding are the ones willing to say 3 simple words. We don't know. Those words open doors. They invite curiosity. They make space for new ideas. They prevent the premature closing of investigations. When you admit uncertainty, you keep the question alive, and living questions eventually find their answers. Consider the researchers who will pick up where current investigations end. Students not yet born will inherit these mysteries. They will bring fresh perspectives and better tools and ideas we cannot anticipate. What seems impossible today may seem obvious to them. What confuses us may clarify for future minds. We are part of a long chain. Earlier links in that chain made errors. They were certain about things that turned out to be wrong. We will make the same kind of errors. We are probably confident about something right now that future generations will find quaint or misguided. That's not a criticism. It's simply the nature of an ongoing process. Science is not a destination. It is a way of traveling. The mysteries we've discussed are not problems to be solved and forgotten. They are invitations. They are the universe asking us questions we don't yet know how to answer. Each one represents something real, something observed, something measured, and each one waits patiently for understanding to catch up. Maybe it will, maybe it won't, but the attempt itself has value. The honest confrontation with what we do not know shapes us. It keeps us humble. It keeps us curious. It reminds us that the cosmos is larger and stranger than any single mind can hold. The mysteries remain. And perhaps that's exactly as it should be. Let that thought settle. We have traveled together through signals that appeared once and never again, through stars that dim in ways physics cannot explain, through circles of radio light larger than galaxies, through structures so vast they should not exist, through voids so empty they feel like wounds in space, through cold spots that whisper of other universes, through elements that refuse to decay, through visitors from other star systems, through explosions that rewrote our understanding of stellar death, through a star older than time itself seems to allow. And here we are, at the end, or perhaps at a beginning. You are alive during a golden age. The James Webb Space Telescope is already sending back images of galaxies that formed too early, galaxies that existed when the universe was too young to have made them. Our rules said, They couldn't be there. They are there anyway. The extremely large telescope will soon open its eye to the sky. It will see deeper and clearer than any instrument humans have ever built, and it will find more. More phenomena that break our current understanding. More observations that make us revise what we thought we knew. This is not a crisis. This is the promise. The universe doesn't care about our expectations. We have said this before, but listen to it differently now. The universe doesn't care about our expectations, not because it is hostile, not because it is indifferent to us, but because it is extending an invitation. Every anomaly is a door. Every mystery is a gift wrapped in confusion. Every observation that refuses to fit our theories is the cosmos saying, "Come closer, look harder, think differently." The phenomena we discussed tonight are not frustrating failures of understanding. They are beautiful invitations to understand more deeply. They are the universe telling us there is still territory to explore, still wonder to experience, still discovery to be made. Future generations may look back at this moment with something like envy. They will know answers we cannot imagine. But we are here at the frontier. We are here when the questions are still fresh. We are here when the data first arrives, and no one yet knows what it means. That is a rare privilege, to stand at the edge of knowledge and feel the ground give way beneath your feet. The stars above you tonight are burning with secrets. Some of those secrets will be unlocked in your lifetime. Some will take generations. Some may wait forever. And all of that is exactly as it should be. Let your eyes close if they haven't already. Let your breathing slow. Let the weight of the day ease from your shoulders. The cosmos will continue its strange and beautiful work while you rest. Galaxies will collide in slow motion. Stars will be born in clouds of gas and dust. Light will travel for billions of years toward eyes that have not yet opened. You are part of this. You are made of elements forged in ancient stars. You are the universe looking back at itself with wonder. Sleep well under the stars.